Hello and welcome to this section of doing performing QSAR using R. So QSAR stands for Quantitative Structure Activity Relationships, where as you have learned in QSAR, compounds have like a lot of properties, molecular weight, topological polar surface area, then log P, then solubility. Also, how this thing, how these properties correlate to activity. So that's a kind of equation we call the multiple linear regression, where what we do is the multiple linear regression model attempts to find a relationship between two or more explanatory variables and a response variable by fitting a linear equation to the observed data. So every value of the independent variable x, which are the molecular properties, is associated with the value of the dependent variable y, which is the activity outcome. So apart from like studying the activity of a specific target, which is called structure activity, we also study QSPR, like quantitative structure property relationships, like the melting point property, like the solubility property, uh, um, uh, like the aquatic tox property, something like that. So the QSPR, QSAR are kind of synonymous, and they are respectively they are commonly used for one for modeling the molecular properties and other for modeling the activity of compounds. So there are various approaches in modeling the QSAR. We will be showing you the basic one, the ordinary least squares, or we call the MLR, the multiple linear regression, which is quite common and it's not widely practiced. And apart from that, I'll be showing you the PLSR, the partial least square regression, where actually it's a extension of the principal component regression, where you decompose the variables using SVD and project into a new space. Both the dependent and the independent variable is projected into a new space. And another one is the ridge regression, where you can estimate the properties, or which estimate which properties are quite good in your model, like which properties to eliminate or which properties to keep for your model. So basically, normal multiple linear regression, there are problems with multicollinearity. So the PLSR and the ridge regression helps you to overcome this multicollinearity problem, and helps to model the data pretty well. So first of all, there's a package. I'll be using some of the codes from the from Max Kuhn, and I had emailed him for some codes, and he supplied me some. And he has this website here and a book Applied Predictive Modeling, where he just used Caret package, and there's a package also, Applied Predictive Modeling package, where I use that package to use some data. And this is quite nice book, where he did a lot of QSR, and also like shows how to do like model using this Caret package, and also gives a very good idea of how to prepare, how to make good predictive models. So you can go to his website and check it out. But I'll be showing you some other some other techniques mostly, and also some plotting techniques, nice visualizations, and help you to explain what's going on. So first of all, for the QSR data, these are the packages: QSR data package, the Caret package, the Gplots. I'll be using to plot the XY, I'll use the XY plot to plot some linear regression plots, or you can say the scatter plots. The lattice extra is a package where you can add extra layer of points on top of the XY plots. And lattice is this is plotting package, and ggplot2 is another visualization. So I'll be using like both of them to show how to plot and how to make nice visualizations and do QSAR. So there are also two functions here, RMSE, mean square error, and the R square, which is commonly, these two are the commonly used, and another one is Kendall tau. So I didn't do it. I want to make it much more simpler. So the RMS is root mean square error, and the R2 is the regression coefficient, is the correlation coefficient. The R squared, like how much. So it ranges between 0 and 1. If it is close to 1, so it indicates okay, your model is predicting pretty good, and it should, and also RMS shows you how much is the error in the prediction set, in the predicted set and the observed set. So both of these matrices are pretty important in the while you do QSR. And this is the plot star function, plots the nice based on the ggplot. It plots nice plots with black background and colorful like points and regression line on top of that. So start with so I'll load the QSAR data package. If you can't load it from CRAN, just download the tar file, the search in Google, the QSAR data package, download a tar file and use a local installation, like go to like tools, install packages, and install the package. So there is a package, there is data sets inside the QSAR data. So I'll be modeling the aquatic tox data set, and you can see, so these are the molecules, these are the activity of the molecules here. It's already logged activity here, and also these are some properties here. So also data set comes with you can search here, and it comes with a lot of descriptors. So it has a lot of featured descriptors like atomic pair descriptors, daylight fingerprints, the dragon descriptors, and this one is these one are pretty quite famous descriptors. It's really good. It comes with MOE fingerprints and descriptors and pipeline palette fingerprints. I think it has the ECFP6, which 1024 bits, and the quick prop. It's the Schrodinger quick prop admin predictor properties, and the aquatic tox outcome. It shows you the activity. So I'll be using one of the small descriptor feature set, which is a quick prop. You can try your hands with other descriptor set to predict. So these are like, some of them are binary values, dichotomous variables, but these are like integer variables, and every column has some nice value like negative, positive, or so I put it into our data, and then I make a data frame of activity, and along with the descriptors, you can see the headers. So all these are the properties of the molecules, and I just used a data frame to add the activity column to it, and you can see the dimensions is like 322 molecules and 51 columns. So I want to change the 51st column of this one to the activity column name, and well, this actually change the activity column name to activity. And if I have some rows which has NA values, I should use NA.omit, which will remove all the rows which contains any NA value. So this one removed all the rows, and then this one remove. So since I removed all the rows containing NA values, if you want, you can remove via column. Like if a column has NA values, you can remove that column from your data set. So this function does that, the first one, and this second one removes the near constant columns. So near constant column, like it contains continuous rows of 1. So those variables are not quite interesting to model. So better you remove them. And then also you can remove the correlated columns. And see, I have used very small, very low correlation coefficient here. and which removes which are I want to remove all the correlated variables which are more than 0.25. So what happens that in doing modeling in using normal regression like multiple linear regression, there is a problem with multicollinearity, so which is a big issue. That's why we'll be using later on PLSAR and the rich regression models, where it actually you can just overcome this multicollinearity problem. But in this case, if you use this one, so it might be possible that suppose you have 4 feature data set like x1, x2, x3 and x4, and x4 variable is kind of dependent upon x1, x2 and x3. So they are maybe a combination of x1 plus x2 into x3. It's kind of very highly correlated to x4. So what happens, like MLR or R will throw you an error like a rank full matrix, that kind of error, which means that it's not using the 4 variables to model. It actually is using the 3 variables to model, and it will throw you an error. So in this case, like I also had that error, so I decreased the correlation coefficient to like 0.25. I had overcome that error. So it's just a basic way to model, and it's just a preliminary basic way. If you like have 10 feature model, 10 features, you can just you just see which is highly correlated and you just remove that, remove one of them. Like if you have one of the variables which are highly correlated, you can remove one of them and try to model. So since it's had like 50, so it's pretty hard to figure out how to use the different functions or different variables to model. So anyhow, a general way, I just used a correlation cutoff of 0.25. So I selected which are the variable names which are highly correlated, and this one does select those variables, and D has the unique. You can Now D has 319. So there were 322 at first, and now 319 means there were some 3 compounds which were having Na values, and now it remained with just 14 variables. So we'll be using these 14 variables to model. Now after this modeling, we need to do the normalization of the data. So normalization, like all the columns should be normalized well, and so I'll be using there are various ways to normalize. You can just do the mean normalization, or use mean and standard deviation to normalize. So I'll be using a well-known normalization function that's what's known as the power transform, which is useful in data transformation technique, used to stabilize variance and make data more normally distributed. So that's the function they have provided is the box-cox, which is a kind of power transform normalization technique. But there are other methods. You can look at that book, Applied Predictive Modeling, and there are also like scale and center methods where they scale the all the variables using like mean and standard deviation normalization. So the preprocess function actually normalizes your data. And see here, I have used 2 means from the second column. Since the first column is the molecule names, we don't take that into like normalization. Doesn't make sense. So, and then use the predict function to uh, to make this. So preprocess actually processes the data, and predict actually helps then uses the t variables to again to normalize your whole data set. So it creates a function, and then it normalizes your data set here. So data is now normalized, and from now I'll create a training and a test set. And for the test, I'll training and test, it's divided into 0.8 and 0.2, and this and the it so train and test set is done, and now used ordinary least squares to model. So I took test set So test set has the activity column. I put it in y.test here, and then just call the lm function here to do ordinary normal least squares on the train set data. So I'm building the model based on the train set, and then we'll test the model based on the test set from here. So you can use the summary results here, and you see the multiple r square is 0.744, adjusted is 0.73. It makes a little bit of correction here, and it shows, you can see the important properties also, like the quick prop ACC THP. So it has very low highly significant probability value here, and this one. So these are the significant descriptors for your data, so which has like very highly significant value. So this shows you which the descriptors are important for modeling here. And then I create I predict the results of the train set. The train set has the observed values. So let me predict that values using the model, because I need to make a plot of the predicted values with the train within the train set and the test set. Okay, I just predicted the train set, observed values, and the test set, and then I create a data frame of the y test with the predicted OLS test, and this R2. So this one returns here uh, the test set R squared and R RMS. It's not, it shows like these are the values. It's pretty quite high, and you can test this code with some other data set or properties and just try to see uh, how does it model. So now comes the plotting. So I used xpy plot, and the as layer will add the test set points to the plot. So you can see plot here. It's a nice plot, and this is the regression line, and the black dots represent the test set and the blue circles represent the training set points. So coming to the partial least squares, partial least squares regression is a statistical method uh, which is a kind of a linear regression model, and which actually projects the predicted variables and the observed variable into a new space. So the projection is based on the SVD. SVD is known as a singular value decomposition, where they actually factorize the matrix. And the PLS regression is particularly suited when the matrix of predictors has more variables than observations. Like if you have like 1000 variables and 300 compounds, and then in that case PLS regression is pretty good, because it reduces the dimension of the the variables, and like just similar to the principal component regression. And also it helps like when we have multicollinearity, like for example in MLR it's very hard to figure out the multicollinearity problem. So PLS reduces this, and so among the X factor variables. Now the difference between, if you can do PCR regression and the PLS regression, the difference with PCR regression is PCR only projects the X factor but not the observed variable, that is the Y, the independent variable, the dependent variable. So in PLS, both of the variables, the dependent and the independent variables, get projected, and like they do the spectral decomposition, or SVD. So for this I install a package, install PLS package, and there is a library, I call the file library here, and again I omitted, I just had the Q data and I omitted, I redo it, these things, and again I pre-process the data, just the old methods, and make a train set of 80 and 20%. Train set X has, and train set Y has the activity train set X, test set Y has the activity of test set, and train Y has the activity of the training set. So I use the PLSR command on the train set X, and then should be 10, Then I just say like model based on the first 10 components. So one this PLS fit is the model, and now what you do, you are just predicting with the test set with the first 10 components, and then predicting the values of the training set with the first 10 components, and then you just summarize the results. So yeah, R squared is pretty better, much better now. It was previously 0.6 here, 0.68, and now it's 0.72. Yeah, so now the thing is, we want to see how many components is kind of good to reduce this RMSE, the root mean square error, and increase the R squared value. So for that, the Caret has provided the PLS tune, which I will show you later, and then I just make the plot and show you. So it's a very nice plot here. I created a function which plots the black points and shows the line, regression line, and the yellow you can see these are the test, and blue are the training set points. So now coming to the point, how do you know which so in this case you don't know how many components is good for your model. So for that, I'll be using the PLS tune kind of like to find out which is the um, how many components kind of require for modeling. So let's see, I use 10 here, and I will also do the cross validation. So the train control, the train method here is used in the Caret package. It's the function used in Caret, and even the train control. So I just say that I need to do cross validation, and with five folds of cross validation. So I prepare it this one, and then call the train function, and tune length indicates the number of components, and pre-process the data with box calls. So it's actually done. You can plot. So you can see the RMSE is still 0.4 here. So you with 10 components, you can decrease it. If you increase it to like 15, you can have a more better RMSE. Yeah, so see, it's much below 0.2, which indicates that the R square RMSE is much well below 0.2, and also we have better R squared. So we will predict the train set and the test set results using the PLS2 what we got here with 15 components. So this we just made a data frame of these values, and now we will calculate the RMSE of the observed and the predicted values of the train set. See, it's 0.99 now, and for the test set is also 0.99. So PLS values 2 indicates the test set, and PLS values 1 indicates the train set. So now we can plot it using this XY plot. It's got very it's kind of nice fitted line. Coming to the regression model which is created, so in the mass library package you have this lm.reg function which also does rich regression. So I'll be using the enet elastic net package, which has the enet function to do the rich regression penalty. So what happens in the various covariance matrix in case of multicollinearity, uh, 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 the covariance means the off diagonal elements, which are the covariance points. It actually the values are much more than the diagonal elements. So what we need to do, we need to increase the diagonal element values. And to increase the diagonal element values, what they did is they just multiply the diagonal elements with some values like 0.001, so that the variance in the diagonal uh, is more than the off diagonal elements. So what they use that term, they call it lambda. So and then what we can see which using that trick we can figure out which are the variables are causing this problem, having high multicollinearity and causing a model to get wacky. And so doing that, I'll be using this applied predictive modeling package. I'll be using a different data set. It's the solubility data set. And now the dataset has this already they generated this train set here, and the train y, which is the train set, is the variables like this is the x variables, and y is the observed value. And so first let's model with this lambda, as we said the lambda is 0.01. How does it model? And just let's see. We can also tune this lambda and just see using which lambda we can get the best model, and use that lambda for predicting. So I'm just using an just an random lambda and trying to do it. We'll use later how to get this lambda using tuning. So rich model is done, and I have tested this with model and with the test set and also the train set. And let's see the r squared. So it's also good. It's 0.9. It's 0.99. So how did I estimate 0.01? 0.01 is really good. So our 0.0 is good. So again, when we plotted the results, oh, it looks really good here. It's kind of too much overfitted maybe. Uh, so for tuning, I'll be using a sequence of lambdas, like from 0 to like 0.0 to 0.1 with a length of 0.15. So it creates a sequence of elements of numbers from 0 to 0.1 with a length of 15, and I'll use all this lambda to train to see which model which lambda we can get the maximum r squared valued. So already I have generated it takes a little bit of time, like 4 or 5 minutes. So I have already generated the rich fit model here, and you can see here after running this thing, you can see the different lambda values, and you can see at 0.692 this one which shows the lambda value which give me the lowest RMSE and the highest r squared values. So I'll use that to do the modeling here. Like I just found which lambda gave me good results. So this 0.2 is good here, and then I predict the test set, then the trend set. So names initpred shows the list of variables it has. Initpred is a list class, and the initpred dollar. So this fit has all the values, the fitted values. So go here. I just made the observed and the predicted fit values of the test set and the train set, also the fit values, and then I just want to see how does the test set values what's the RMSE of the test set. So it's like 0.878 of the test set. So we just bind this to and plot the SAR, plot the results here. Now, to determine which predictors are used in the model, we can use this function, like we can get the type. Like first we got the fit, which fits the model, and if you change it to coefficients, it will give you you can just plot the which you can just show the coefficients which are important, like which have been used to model. So these are the important factors. The tail gives you the top five elements which were required to model this ridge regression model. Please try the code by yourself and try to figure out what's going on. I hope you like the QSAR lecture. This handy tutorial will help you to do a lot of handy work in industry or even in academia.